All right, welcome to Module 10. We're going to be talking about air currents as they relate to the unequal heating of Earth. To start off, we'll be talking about the four properties of air, and those properties are density, water vapor capacity, adiabatic heating and cooling, and latent heat release. So the first one, warm air has a lower density than cold. Why is that though? Well, as air becomes warmer, air molecules gain energy and therefore move more quickly. This causes warm air molecules to be less densely packed than cold air molecules, which results in a lower density of warm air. Here's my picture of a bunk bed. So if you've ever slept in a bunk bed, you know that the top bunk can be very hot. And this air is less dense than the bottom bunk, and the bottom bunk has more dense air that is less hot or cooler, and the warm air is rising. This is also true in a two-story house. If you have a two-story house, you know that it is harder to keep the second story cool in the summertime. All right, the second one we'll be talking about, water vapor capacity. This graph does a great job of showing that as the temperature drops, so too will the saturation points. To remember this relationship between temperature and the capacity of air to contain water vapor, I like to think hot and humid or cool and crisp. All right, the third one we'll be talking about is adiabatic heating and cooling. So for this one, remember the ideal gas law that you learned in physics or chemistry? In this equation, you notice that if pressure was to increase, so too would temperature. So let's look at adiabatic cooling. It's the cooling effect of reduced pressure, so decreased pressure, on air as it rises in the atmosphere and expands. So this would cause the temperature to cool. Adiabatic heating is the heating effect of increased pressure as pressure goes up on air as it sinks toward the surface of the earth and decreases in volume, which would cause the temperature to go up. And finally, latent heat. So to talk about latent heat, I drew you another great picture. This is my ice cube as it's melting. So the word latent means hidden. So sometimes you'll hear somebody say that guy's got latent talent or latent capacity. So it's hidden talent, hidden capacity. So why would heat be hidden though? Well, latent heat refers to phase change or state change, like for example a solid to a liquid like I've got here, or a gas to a liquid. When phase change occurs, the temperature actually remains constant. But why is that? Well, here are a few. This is a solid with all the molecules tightly packed, liquid less tightly packed, and gas much less tightly packed. So when you heat something, you're actually adding kinetic energy to increase the temperature. But in a phase change, all that kinetic energy added is used to make the molecules come closer together or spread apart, depending on which direction you're going. So for example, if I was moving from a solid to a liquid or liquid to a gas, all the kinetic energy that I put into the system to heat it up would be used to oppose that intermolecular force of attraction and spread those molecules out. So phase changes occur at a constant temperature, and that is called latent heat. And when latent heat, as we're talking about the atmosphere, when water vapor is in the atmosphere is condensed into liquid water, energy is released as heat, and this heat release is called latent heat release. Whenever water vapor in the atmosphere condenses, the air will become warmer and it will rise into the atmosphere. So these are the four properties of air that we're discussing, and it is these properties of air, as well as the Earth's rotation, that fuel all of atmospheric convection currents, which is what we're going to be moving on to now. So here's a convection current. There's one picture of a current and how that works. Here is a flow chart of the whole process. So these are the processes that create atmospheric currents. So warm air rises, which leads to pressure decreases, which leads to air rises, which causes lower atmospheric pressure, and then causes adiabatic cooling. Remember, the PV equals nRT. And then it reaches its saturation point and condensation and precipitation occurs. Then there's a latent heat release when the water vapor in the atmosphere condenses into liquid water and energy is released as heat. This will offset some of the adiabatic cooling that we saw here. So the warm air warms and then rises some more, and then lower atmospheric pressure. Then there's an adiabatic cooling. Then there's a horizontal displacement and sinking. So as it reaches some height in the atmosphere, it starts to move horizontally and sink. So there's nowhere else to go, so it starts to move horizontally, also due to gravity. Then there's a higher atmospheric pressure, and again adiabatic warming, which brings us all the way back up to the top where we've got air warms, pressure decreases. So this is how this cycle happens. Another thing that I wanted to show you before we move over to my map is the intertropical convergence zone. So this is what the intertropical convergence zone looks like. It's not a straight line like the equator. It kind of moves up and down a little bit over that. And that is what makes the tropics experience seasons of high and low precipitation. Also, the Hadley cell, which we'll be talking about when we look at my graph together, the Hadley cell is from an area of 30 degrees north and 30 degrees south. But after the tropical air loses its moisture and sinks back to Earth, right at about the 30 degrees north and 30 degrees south, it becomes warm and dry. So the regions right there are typically very warm, hot, dry deserts. So that makes us in San Diego at 32 degrees north, makes it very warm for us. And the regions of intense sunlight will be around the equator, which is around 23.5 north to 23.5 south. And that's where most of the rainforests occur. So these Hadley cell, or I'm sorry, these convection currents in these cells make up the weather in the atmosphere. Okay, heated air expands and becomes less dense. So molecules have to move, can move around each other without touching, and they don't put pressure on each other. So the air is always going to move from an area of high pressure, where it's cold, to an area of low pressure, where it's much warmer. In just a moment, we're going to move over to my map, so I wanted to start off with these things so that you feel comfortable with it. So here's a picture of the Earth. Due to the Coriolis effect, so we have a high temperature where it's cold at the top, low pressure at the equator, high pressure again at the poles. Due to the Coriolis effect, as the wind is moving from high to low, it turns to the right. Now you might think this actually looks like it turns to the left, but you have to kind of pretend you are the wind. So it's pointing down. If you were to look down and go off to the right, that's what's happening here. But if you were in the southern hemisphere, it turns off to the left. I'm going to pause here and move us over to my globe. All right, looking here at the globe, you'll see that we have a high pressure system at the pole, low pressure because of the heat at the equator, and then another high at this other pole. So if I'm driving my car, my orange sports car, if I was to just drive from the high temperature down to the low in a straight line, notice that I would get from my little tape thing to the other tape in a straight line. But what's really happening is the Earth is turning, right? So as the Earth is turning, I'm going to continue to drive this Hot Wheels in a straight line, but I'm turning the globe. So this is what I mean by it's turning to the right. Imagine you're driving this Hot Wheel and you would be turning your car to the right. So again, we go from high to low, but the Earth is turning, so we end up well away from this spot. Now, why is it different in the southern hemisphere? Well, let's try it. Again, if we went from the high to the low in a straight line, we would go right away, but we're going to be moving, and it's going the opposite direction, isn't it? But the Earth is turning the same direction. So that's why, that's the Coriolis effect, as the effect of the Earth's rotation.